Well, hello everybody and welcome back. So as you can see on our bench, we have a new member of the bench, and it is a Leader model LSG-216 standard signal generator. And I've been looking for a good one of these for a long time. This is going to make my job a lot easier working on receivers, simply because of the way this thing's laid out. It actually is a signal generator that is dedicated to working on AM/FM broadcast band receivers, both mono and stereo. A couple really nice features. It reads directly out in dBu or dB microvolts. You can turn it does internal modulation both with FM, AM, pilot. It'll do multiplex stereo. You can modulate it at 400 Hertz or 1 kilohertz. Everything is all completely built right in. You can set the percentage of modulation with this nice little analog meter, which I like. It has two different frequency ranges. It is absolutely exactly what I wanted, and took a long time to find a good one of these. They don't come up very often. Both Leader and Sencor equipment I really like. It's very good quality. It's really geared towards the repair bench. It's definitely not laboratory grade, but this is a synthesized signal generator, so it's pretty accurate, and I already ran it through its paces. I tested it with my high resolution frequency counter, and it is absolutely spot on all across the band. So you'll be seeing a lot of this in future videos. I then just took and moved the B&K 1655 back up to where it originally was. So our isolation transformer slash variac. And another great thing that I did was I got a nice new, as I'm moving my camera around, a new camera mount arm. And you can see when I let it go, it is rock solid. That other one was just terrible, and I apologize for those last two series of videos that I did. I was just so busy I could not get that stupid thing out and replaced. But, you know, I had to get something because the original camera mount I was using was really in my way, and it was really worn out and starting to slip and so forth. Had to do something. I finally broke down and bought a Manfrotto articulating arm, and I couldn't be happier with it. Had to get kind of creative with the mounting, but I think it'll let me get the camera in some pretty good positions, but still keep out of my way enough that I can still work on my bench without banging my head on the camera all the time. And more importantly, it's not going to be like a pendulum swinging back and forth like that that other arm that I tried. It just wasn't substantial enough. So hopefully we'll get some better video quality that is a little more stable. Anything's going to move. That, you know, this Sony camera is kind of heavy, and it's still on an arm. So if I bang the arm a little bit, you know, you can see it'll shake a little bit, but you can see it'll stop very quickly too. So hopefully this will be it. All right, let's get on with our new project. What are we going to do? So as you can see, I actually have a STK module on the bench here, and this is an authentic one. This is a real one. It's been pulled out of a good working receiver. This one's a stereo module, a 2040. It's a 40 watt per channel, 2-channel stereo module. These were made by Sanyo, and Sanyo back in the 1980s made an entire series of these, and they're all very similar, with the exception of some are 2-channel, some are 1-channel, and the different wattages. So you can get the small ones all the way up to, you know, over 100 watts. And the nice thing is many of them have the same pinout, with the only difference being the amount of power they can dissipate. So the problem was these were very good modules. There's a lot of misinformation out there about them. And there's also a lot of counterfeit units out there today. These are no longer in production. You cannot get them from the original manufacturer, and a lot of the new ones, quote unquote, that are out there are knockoffs, and they're very poor knockoffs because they're not built like an actual integrated circuit like these ones are. So you may be asking, why are you showing me this chip? What significance is this? Well, some very enterprising individual who has posted a whole 30-some page article thread on the Audio Karma website has actually come up with a good solution to replacing these modules. Now, not this one because it's stereo, but the original ones like the STK-0050, 0040, and so forth, the 0080. These are all the same pinout, and he actually came up with something that can replace the chip but use discrete components. Now, this is really important because the receiver that we're going to work on in this video is a Pioneer model SX-780. It was a very popular receiver. Actually, if you read the Silver Pioneer reference site, which is a great website, it kind of moves around and comes and goes, and sometimes you can find it and sometimes it goes off air. But it's a website dedicated to the silver-faced Pioneer receivers and amplifiers and audio gear especially from the 1970s era and into the early 80s. And the SX-780 was actually one of the most highest produced number of receivers that Pioneer ever built. They built tons of them, and they sold huge numbers of them. They were fantastic receivers, and they used an STK-0050 module. It was rated at 45 watts per channel, and they used 50 watt modules. They were exceptionally good sounding and very clean. However, when the chip failed, you were out of luck. Until now. So what this is a couple of little circuit boards and a couple of little aluminum plates that actually, when we populate them with the components, will simulate the STK module, and more importantly, we'll be able to mount this right in place of the old STK chip. So if that sounds good to you or sounds interesting, stick with me, because on this video, that's what we're going to do. We're going to build these up, and then we're going to rebuild an SX-780 Pioneer receiver. And then we're going to test it out and see how it works. Now, before I continue here with the project, I'll try to answer two questions before you guys even ask them about the signal generators. Question number one, no, I am not going to sell the SG-165 or my Sound Technologies 1000A. I'm going to hang on to them because I will still use them. And number two, I will in fact go through and do a video on each of them, just a short one, like how to use them. Because I know a lot of you have one or the other, and they're very good pieces of test equipment. So I will do that for you. I've promised a few of my viewers out there, of you guys already, that I would do that, and I will do that. Just need to get some of these other projects through here and off of the bench, and then we'll do it. So anyway, let's continue. If you want to purchase one of these modules after watching this video, here is the eBay channel that you can, or site that you can order it from. The seller is, you can see, Bob and Elaine Pike. And no, I'm not getting an endorsement from this. Actually, one of my viewers turned me on to this and asked me if I would do this for their SX-780, and I have owned an SX-780 of my own for about 30 plus years, and I really like it. So this looked like a really interesting project, and I purchased one to try for myself, and he purchased one to have me put into his receiver. So no endorsements, just an interesting project that I thought we'd try here. This is what the module looks like assembled. where this would normally be mounted on here, you have this. And if you look down here, don't be deceived. Here's one listed on eBay, an 0050, which is what belongs in the SX-780, for $19. I guarantee you they are not real. They are phony and they don't work. Now, if you're interested in more information about this, here is the heading of the thread from Audio Karma. And if you just Google search this, the first thing that pops up on Google is this thread. And it goes through and gives you all kinds of very valuable information about this whole project and how it works. So check that out again, and let's get started. So the first thing you're going to want to do when you order one of these is these do not come with the components. You just get the aluminum plates and you get the 2 circuit boards, and you do get some hardware. But other than that, the components you have to order. Now, luckily, what they did was on the same website where you order this, right on eBay, if you go down into the item description, or if you go to page 1 of the actual book, or the actual Audio Karma site, they actually have a link to a shopping cart or an actual list here where you can get the components and from Mausers, and you can order them. But if you download the bill of materials from the Audio Karma page, all you have to do, it's a one-click thing. You click on it, it puts it all in a shopping cart, and you can just order it and they'll mail it to you. So you will need to order all those parts. And I would suggest kind of reading through, because there are a few notes on some of the different replacements for the transistors and things, a couple different options, and you can read on that. But you can order them all in, and then you just kind of want to sort through everything, and we can start building it. Now you can see here what we're going to be building. It's actually a pretty simple circuit, and when you look at it, it looks like a common push-pull output section from any other standard 50-watt amplifier that you would see out there. You can see your complementary output transistors, an NPN and a PNP. You have your drivers, and you have your pre-driver here and phase splitter. That's it. It's actually a pretty simple circuit. This, again, you can download all of this. What I did was I kind of compiled all the notes and all the things from the eBay description and so forth, copied them all in, and created a little PDF with everything on it. And it just makes it easier to kind of have everything in one file. And then I just printed it out. Along with that, I copied all the photographs so that you kind of have an idea of what this is supposed to look like when it's assembled. So there you go. So let me get started on building this, and we'll be back. Okay, let's see if we can get it to focus here. So there's where we are so far with the board, and we're ready to mount the transistors, but you really kind of have to put them on the base plate before, to get the leads the proper length and bend and so forth. If you notice, my hands are filthy, and the reason being is when you get these aluminum blocks, you can see they're very scratchy looking. They don't have a really good finish. So what we're going to do here is we're actually going to lap them down until they're polished. And in order to do that, I'm just kind of using my sharpening stone, or my flat surface stone, which is actually from my shop. It's what I use to sharpen my chisels and my plane irons and so forth. And I started the first one, and I'm just on the first grit of paper, but if you notice, you see when I shine the light on there, it's polishing the edges here, but the center is not polished. And if you flip it around and look at the other side, hold on. Let me clean it off a little bit. if you look on that side, it's the opposite. The center part is polished, but the sides are not. Now what that's going to do is when you go to bolt this down to the heatsink in the receiver, it's not going to sit flush. And also you're not going to get the best possible contact. Basically you're going to have to use the heatsink grease to kind of fill in those gaps. So we polish it, and that will help it to make better heat transfer and better contact. Okay, we got them all polished up, and they're flat now. They're dead flat. And I just took a little countersink and just the 3 holes, just kind of tapered them in just a little bit so they don't, so when you push the screw through it doesn't make a burr. And that's about it. Now they're still rough on the sides, but I'm not so concerned about that because that really doesn't have anything to do with the heatsink or anything like that. So, but there we go. So this is all set to go, and now we can start mounting the transistors. Okay, so we got our first module all put together, you can see, and it looks really good. Turned out nice. So what we're going to do now is we're going to assemble this second one here. And you can see that I've laid out the components. Now it's really important that you do not mix up the transistors because they all look the same but they're different. So what I did on mine was I actually marked right here in those little white silk screened areas, I actually marked the PNP and the NPN side. And then I made sure that I got these correct so that I matched the correct transistors to each of the positions where they belong. Now, what they're having us do is instead of using mica pads and heatsink grease, which would work perfectly well, they're having us use these little sill pads. And you can see here's the ones for the bigger transistors, and here's the ones for the driver transistors. And you can see. And contrary to popular belief, sill pads are every bit as good as the mica and heatsink grease. As a matter of fact, they're probably a little simpler. The only problem with them is they are a little bit delicate, and if you over tighten the transistor or you pull up on it or something, they can tear. So you just have to be careful when you do this, and I'll show you how to do it. And when you're working with the heatsink grease and the mica, it's tempting to sometimes put either too much or not enough of the grease on there. The other thing is, one of the reasons we went and worked these down flat and polished them was sill pads work really, really well on a polished heatsink surface like this, but they do not work as well when there's scratches in the heatsink. You should never really have scratches, but unfortunately some heatsinks are not as polished off as other ones. And in those cases, the heatsink grease actually is a little bit better because it can kind of get down into the cracks and crevices there, into those little micro scratches. It's still not the right thing to do because if the grease gets too thick, it actually is counterproductive. It actually acts more like an insulator than it does a conductor of heat. But the idea is we just want good thermal coupling between all the transistor devices and this aluminum plate. So the first thing we're going to start out with is we're going to take our anhydrous isopropyl alcohol, and we're going to just put a little bit on here, and we're just going to clean up any of the oils or residue off of the heatsink. You don't really want that on there. And then I'll just kind of go through and clean off the back of the transistors a little bit, although they're pretty good. I mean, not really necessary, just in case. Now, by far, for building these modules, the most difficult thing is gauging where you bend these little leads up. As you notice, you have to bend them in such a way that they fit right into these holes. And what I found is if you bend them just maybe a millimeter, or maybe not quite a millimeter beyond where they go down from the wider width to the narrower. So right here at this joint, where it goes from the wider to the narrower, if you go down maybe about 1 millimeter from there and kind of bend them up, and what I do is I'll bend them so that they're a little bit of an angle. Let me show you. So the other thing is, notice your pliers are tapered. So if you hold them in a straight line, you're not going to bend these leads all the same length. So you have to line up the edge of this so that it's straight, kind of like that. See how I have it? And then what you're going to do is just nice and roll it right up, real nice and easy, and leave it at a bit of an angle like that. I'll show you why here in a minute. And we're going to do that to all 4 of them, and then I'll be right back. Now another thing you're going to notice here, and we're going to talk about these insulators because I always get questions about them. If you look, here's the metal tab that's connected to the transistor. This is what actually transfers the heat from the transistor to the heatsink. But if you notice, there's like a plastic ring inside here, and that goes all the way through the transistor to the front. And the reason for that is when we put this screw through here, notice that the screw does not make contact with that tab. This tab is actually connected to the collector of the transistor. So anything that touches this is touching the collector of the transistor. So that's what we want to do, is isolate that from this metal plate. We don't want to short anything through this plate. And that's what this sill pad's all about. Not only is it a very good conductor of heat, it is a very poor conductor of electricity. So when you put it on there, you see that prevents the transistor from actually touching the plate physically, but it allows the heat to pass right through. Sorry, bumped the camera. So I'm not going to put those on right now. We're just going to get this lined up and kind of do a dry run, and we're going to bend our leads and get them to the right shape. So what you want to do is just kind of loosely, you don't have to crank these in, just put them so that you can feel it, the screw bottoming out, but yet you can still move these around a little bit. And we're going to put all 4 of them into their positions where they belong. Because remember, these aren't perfect. I mean, this is machined, but it can be a little bit off. So we're going to get that started. Now, with these, it's a different story. If you notice, this tab is all one solid piece. This is also the collector. Anything that touches this touches the collector. And obviously, if I put this screw in here, it doesn't matter if I have a sill pad in there or not. The screw's going to touch this tab, and then it's going to screw right into this metal plate. So in order to isolate that, this tab is actually drilled at the factory a little bit larger than an M3 metric screw. And it allows you to accommodate this little shoulder washer. If you look at these washers, they actually have a little shoulder on the side of them, you see? I don't know if you could see that or not, but there's like a little shoulder on them. And the purpose for that is it goes inside here, and that shoulder goes inside that tab hole and prevents the screw from actually touching. So when we put our sill pad on, notice there's a gap all the way around there. And that's that little shoulder washer inside there. And then you put your sill pad on top of this and then put it down. Again, I'm not going to put it on for this dry run because all we're doing right now is just measuring up to get our leads bent in the correct shape so everything fits. So we're going to put all these on. And again, I'm not really tightening anything down really tight. And this is kind of awkward for me because I'm working around the camera here. So, not easy, guys. A lot easier when you don't have a camera. Okay. So, that's really all we're looking for right now, is just kind of roughly line them up. And then what we're going to do one at a time, and I don't know if I can do this on the camera or not. I placed this first one in here already. And notice it's bent at an angle, so when it flexes down, it's going to kind of fold into place. And that's the whole idea of getting these leads to line up. I'm going to try a little bit of this on camera, but I don't know how easy it's going to be. So what we're going to do because we're going to kind of like, we're going to eyeball this, and I can't do it around the camera, but I'm going to kind of bend these leads up a little and keep checking until it all lines up. Okay, so there's one, and then just keep bending, and there's the other one. And I'm really struggling here with the camera in my way because I can't see. Here we go. So there's the first one, but if you notice, it's sitting at a funny angle. So now we want to kind of work the leads till everything's nice and straight. And we still haven't done the other side yet. So now we're going to turn this around this way. And we're going to do the same thing with these. We're going to go in, and we're going to start to get these leads lined up. There's one side, and there's the other. And again, I'm just going to push this all down. Now that we have everything roughly in, we'll take this center one and just kind of mount it like this and get the screw started on it. Okay, and notice I'm not tightening anything yet. We're just getting everything how we like it. And see, now it's all straight. Now I'm going to snug these screws a little more. Not much, just a tiny bit, so that it kind of locks them into place. Okay. Check it for straight. Looks pretty good. Now we're going to solder them in. Okay. And the idea is to make sure this board is well seated. You want it to kind of be flush against these, just like so. And we'll go through and we'll tack these all down. And I don't mind my bad soldering job here working around the camera. I'm kind of struggling there. Okay. And then I'm going to have to heat this side back up a little bit to get it to drop. There we go. Okay. It's all sitting flush. Now I'll go through and I'll finish these all off, and I'll be right back. Okay, now that everything's tacked down and kind of bent into place, we can take the screws back out and get all of our pads in place and put everything down. Just like so. So far, I really like this little kit. It looked really interesting online, and when I checked the Audio Karma website out on it, there was a lot of really good conversation on there, so I thought, you know, this might be a good project for us to try. And you know, this is something I think any of you can do out there. Not a whole lot of components involved, and not too bad assembly, so I think it should be a pretty good project. And SX-780 receivers are pretty plentiful out there. Like I said, that was one of the most mass-produced receivers that Pioneer ever made, and they were really a good receiver. I mean, everything about them, I really like them. And don't underestimate those STK chips, the original ones. The actual ones from Sanyo were very high quality. They sounded excellent and they performed very well. On paper, anyway, this one is supposed to perform even better. So instead of using a sill pad in here, I will put a little bit of heatsink grease on that little transistor. Now, that's not a big deal, because all you need is a little bit of coupling grease on there, just a little dab, and it'll kind of spread itself on there. There you go, just like that. And then once you put it on there, it'll kind of squish down and spread out. And the reason for that is these transistors here are plastic all the way around. There is no exposed metal, so you don't really need an insulator because of that. So that makes this one really easy to do. So now that everything's down, what we're going to do is, I'm not going to over tighten these, but instead I'm just going to put a little drop of thread locker on the threads of each of these screws, and then I'm going to put this in here, oops, around the camera. And then, of course, not very graceful now, is it? Okay, here we go. And again, I'm not going to tighten it till I get everything lined up. These sill pads have to be straight underneath. You don't want the sill pads to be like at any kind of an angle or anything. You want them lined up properly. I'm going to take another little drop of thread lock for this one. I hope I'm staying in camera. I can't really see the viewfinder. All right, and we have our little shoulder washer, remember, for these transistors. Okay, just like that. And again, we're not tightening it yet. And then we're going to check these. You can see this one kind of needs shifted just a little bit to get it right. There we go. I'll put a little drop of thread locker. And you don't need much, just a tiny little drop. Just enough to keep the screws from backing out. There we go. A little too much. As I bang the camera again. Okay. And then last but not least, we'll put our little center one in. All right. And now we can just snug them just a little bit. And you notice I'm just kind of using finger tight. I'm not crushing down on it. And I did use a little, these little washers here, which are just fine. These little fiber washers. They kind of keep you from cracking the plastic here by over tightening it. So it kind of gives you a little bit of cushion, but yet it still puts some pressure on there. And this screw doesn't feel like it's holding very well. So we'll have to check that out. Maybe that little piece of aluminum needs retapped. Let me check that out. Okay, change of plans here. I decided to go without these little fiber washers because they were just holding it up by about 2 more threads. And you could see without the fiber washers, you can see the threads almost come down flush to here, but not quite. With them, it raised it up just a couple more threads, and you didn't get as good of a bite on it. So with the thread locker and without tightening these super tight, I think we'll still be okay without those little fiber washers. Actually, they didn't call for them in the instructions. I was going to add them anyways. So no harm, no foul. But I figure that's a little better thing. That's one of the only problems is these screws are so small and they're tapping directly into aluminum. And of course, you know, the aluminum's not that good for tapping out with fine threads. So again, be careful not to over tighten any of these. So that's it. It's all set. We're ready to get our receiver out and start looking at it. Oh, we almost forgot one last thing here. You always, when you mount transistors to a conductive surface like an aluminum heatsink, you want to always make sure that your insulators are in there correctly. So if everything is correct, I should be able to touch the aluminum here and touch the tab of the transistor, and it should read 0. It should not read a short. And you can see 13 mega ohms. And again, and I should also be able to read from this, but if I read from the screw to the aluminum, you see it's a dead short because the screw is screwed into this aluminum. So you can even check from the screw to here, and again, it's mega ohms. So nothing, nothing, nothing. So these are all good. Now we check this one. And again, depending how hard I push and things like that, it'll read different versions of mega ohms, but it's always in the mega ohms, very, very high. A short would look like this. Okay, and there you go. So they're all good. So there are no shorts between our insulators and the heatsink. So we're all set. Okay, there it is. She ain't a beauty, but she's all in one piece. The faceplate's actually really nice on it. The knobs look really good. This has an aftermarket cover on it. And it's made out of, looks like solid walnut, but you can see how this, I think they drilled the screw holes kind of crooked. You can see the screw kind of going in at a side angle like that. But we'll see what we can do with it. A couple nice little pieces of walnut though. The top has come detached. You can kind of see that kind of broke off. And the owner told me about all this. So not much in the line of a cover, but everything else looks to be here. A couple of these little switches look like they got bent in shipping. And that's pretty common on this. It's really hard to pack these things perfectly. There are some people out there that get it just right, but usually it's not the easiest thing to get these packed so you don't bend these little things. They're so delicate and fragile. But anyway, should be good. So let's get this apart, give it the once over, and then we'll see if the thing even works before we do any modifications. Okay, immediately upon first look, I noticed something that looked really weird. I don't know why my eye went to it right away. But if we zoom in, if you look right here, see that little thing that looks like a crack? It's not. It's actually a piece of wire. And it's soldered right here. It wraps up over top of here and down, and then it's soldered right on the other side. So this current limiting resistor has been jumpered out. Yow, that's scary. Typical crud as you're used to seeing on these all the time. These bulbs are really blackened. They might or might not be burnt out, but I'm not even going to turn this thing on. When I see things like this, I don't even want anything to do with it. Most likely, even if this Darlington pack here, if this STK chip is good underneath here, it's probably has some kind of problem or has been already stress damaged because this resistor blew. If these resistors blow, that means that the transistors in here or that Darlington pack has had excessive current through it. That's the only reason that would pop. So right there's a problem right off the bat. So we'll continue looking and see what else we can find here. Okay, so I've removed the bottom to take a look underneath, and before I like to plug anything in or do anything like that, I just wanted to check the fuse. And the first thing I noticed, well, first of all, it's kind of chewed up, so you know that they've been in there before. But the thing that concerns me more is if you look here, it is set to 110 volts, which is not correct, at least if this is being used here in the States, and I'll show you why. Let's check this fuse without me banging into the camera too much. Let's see. All right. Isn't this exciting watching me take a fuse out? If there is a fuse, oh yeah, it's inside there. Okay, and it says it should be a 4 amp fuse, and we actually have a 4 amp fuse. Nice. Okay, so that's good. But this is a multi-powered unit. In other words, this transformer can accommodate different voltages for different countries. If we pull this little plug out, this is a jumper plug, and if you notice, here are the 4 voltages. You can have 110, 120, 220, and 240. And it was set to 110, but here in the United States, typical line voltage is anywhere from 120 to 125 volts. So what's that do? Well, probably wouldn't damage the unit, I don't think. I don't know. But if you put a higher voltage into the primary than what it's designed for, you're obviously going to, number one, overload the primary, but more importantly, your output voltage from the secondary is going to be higher. And as a result, your DC rail is going to be higher. Remember, these are not regulated power supplies. So your main rail voltages are being unregulated are going to be higher. Now, a lot of the times the capacitors in these things are rated very close to what the voltage is. Not always, but sometimes. So you really, this should have been at 120. So we're going to fix that right now just by moving this little jumper. Let's see here. There we go. And now it's plugged to 120, which is where it should be. The other thing is, with this being at 110, if this were plugged into a 120 volt power supply, or AC mains, no wonder that that current limiting resistor popped. It probably was being overloaded, especially if they were running this thing at high volumes. That could possibly be why that happened. Now, again, we don't know I don't know anything about this receiver. I don't know if it works or not or anything. I haven't even plugged it in yet. But now this is fixed, so we can turn it around and be safe to plug in. And again, we're still going to use a current limiter. We could use a variac and so forth. I'm not going to bother with that. I'm just going to use a dim bulb. Just a lot easier for this thing. So let me get it flipped around here and facing us, and then we will proceed. Okay, we got it turned around now, and just giving it a quick once over. And first I looked at this and noticed that these 2 pins were not soldered in, but then after looking it up, these pins here in the middle are not connected. The only pins that are used in these STK-0050s is pins 1, 2, 3, and 8, 9, and 10. Pins 1 and 10 are the inputs. Pins 2 and 9 are the voltages, your DC rail plus and minus voltage. And then pins 3 and 8 are the outputs that will go to your current limiting resistors and out to the speakers. So technically these don't need to be soldered in here, but on this other chip they are. The other thing I noticed is these were soldered on the binding posts, These ones are just wire wrapped. So looks like these chips have been removed and either swapped around or replaced or tested or something. But this has been worked on in the past. But nothing looks burned or anything like that, so we're gonna go with our dim bulb tester. We're gonna plug this in, and we're just gonna do a quick test of our DC rails and see if we get power. Okay, we have our meter. We have the unit plugged into the dim bulb. We're going to turn the power on, and we're just going to see if we even get power and get Protect relay to come out. Let's see. Oh, Protect relay popped. Okay, good. All right, so now let's find a nice convenient ground. I think there's a terminal here. See if that's a ground. Let's check our B+. 37 volts, and our B-, negative 37. So that's good. And of course these are tied in parallel, so they should both read as well, and they do. So good, we have power going into these chips. Let's hook up a set of speakers. Well, actually, I'm going to hook up the dummy load, and we're going to look at the scope and see if we can drive a signal into it and if it'll make sound. Okay, so I have a dummy load connected, and we have our scope connected to the test points, and we're still on our current limiter. All right, that's good. And I'm going to go to full power now just to make sure everything's still working. And our idle current's about 270 milliamps, which sounds about right. So let's bring our volume up, and I have a 1 kilohertz tone. There's our fundamental. You can see the FFT. And I'm looking at the power meters on the receiver, and we're doing 25 watts per channel right now. And everything looks to be good. And there's clipping. So the amplifier is working. Actually, it's working perfectly, so that is a good sign. So I'm not going to go crazy on doing any restoring or changing anything. We just want to take these chips out and put our new modules in and see if it works. I don't want to introduce any other variables. We know we have a working receiver. We know the voltages are all good. So we're just going to go ahead and try that out and put our modules in. Okay, so we've got the first chip removed here, and I just started cleaning this off a little bit. And as you notice, this new module won't fit. And the reason being is that these two little screws are sticking through here. And what these are is there's actually a backer plate that is used to kind of give a little more thermal mass to this heatsink. Now, of course, this comes with its own backer plate, so we're not going to need that anymore, so we can flip this around and remove it, which is what we're going to do. Okay, and these are the two little plates that were kind of stuck underneath, and you can still have the heatsink grease on them. And now, if we take our module, should fit right on there, and it does. So let's get this mounted up, and we'll be right back. Okay, we got one mounted, and then this other one, we just put a nice fresh coat of heatsink compound on it, and we've lined up the holes. And these mounting holes line up with the original mounting holes for the chip. And we use just the original mounting screws. Drop them in there. And it's just as simple as that. Here we go. That one. And this one. Okay. Of course, don't over crush it too much. Those have lock washers, so they'll hold on pretty good. Okay, now we're ready to connect the wires, and I'll show you that in just a minute. Okay, I've begun wiring this up, and the way I'm doing it is I'm just using number 22 gauge solid tinned bus wire, and I just take a little length and just kind of cut it roughly, and then I give it a little bend. And again, I'm working around the camera, so it's a little bit awkward here, but forgive me for that. And then we're going to go here, and the first thing we want to do is solder this side down. Alright. There we go. And then what I'm using is this Ptfe Teflon tubing. And this stuff is very, very heat resistant, and has a nice, pretty high dielectric content, so it's actually very durable. It doesn't cut very easily. It doesn't crack when it's flexed and bent. So it's all good stuff. So basically I'll take it like that and just put a little length on, about half an inch or so. And just cut and leave a little end out like that. Then you want to kind of bend and put like a little knee in it, like this. And you want to leave the wire exposed a wee little bit above the board, just kind of like that. And then we want to just go in and fill in that little socket. Just like so. And what that does is that gives you some flex, because if you notice, this board can flex, so you kind of want to have a little bit of a knee there for this wire to kind of flex a little bit, so it doesn't pull and break or whatever. So we're going to finish that up, and then we'll be back. Okay, so I'm now down to this one right here, and if you notice, this one's been soldered on, and when I took this out of here, you can see this is kind of cracked out in here, and that kind of makes sense because that pin was kind of bent over and tacked on there. So let's see how we can fix this. Now, of course, one way is I can strip this back and just lay the wire over there and kind of bodge it on that way. Let's see if there's a little better way we can do this. Okay, so we can make our own little repair tracks using this, and if you notice, this is I picked this up at a hobby shop. Actually, I got it at a place called Patka, but there's any hobby store, you can usually find this, and it's used in arts and crafts. And what it is this just a roll, let's see if I can get it out of here, of copper sheeting. It's very thin. It's just like a foil, and you can see how much you get, and this is only a couple of dollars. And one roll of this will last a very long time. So all you do is just cut a little piece off, and we're just going to make our own little repair track. So I'm going to try to do this on camera as best as possible, but working around here can be kind of difficult. But the first thing you want to do is just start out with a small piece like this, and you want to kind of make the rough shape of what you're trying to do. And actually what I'm going to do is I'm going to put something down over here, because I certainly don't want to drop any little pieces of metal down in this. And we're just going to take and kind of cut this round. I don't know if I'm going off frame or not, but we'll try not to. And we just cut that down. So you start out with a little piece that's roughly the width of what you need. So we're just going to kind of go in here, and you can see that's pretty close. You can't see here, can you? I'm in the way. But let's see there. So we're going to just narrow it just a little bit more. Sorry, I'm kind of off camera, but it's kind of hard to do this. Alright. And then we're just going to cut it off to length. And there you go. That's it. Now then, the next thing you want to do is we want to put a hole in it. And to do that, we're going to use a little tool here called a pin vise. It's just got a little chuck in the end. And you can put a small drill bit in it. And by the way, I bought this also at the craft store. You can get these. They're very inexpensive. Again, they use them for crafts and arts and crafts things. And we can use this to poke a little hole in the end of it. Okay, we're just going to put a little piece of cardboard as a backer. And cut the little hole. Just like that. And hold on, I'm kind of got to get it here where I can. There it is. Okay. And if you don't make a mess of it like I did, you have a little hole in it like that. Okay. Try to do a neater job than me and try not to do it around a camera. Now the next thing we want to do, I'm going to put this off to the side, is we just want to take and clear off the solder mask right here. So that we have something to adhere to. And then we're just going to put this right in here. And when we're done, we'll cut it off to size. So you can see that's a little bit big. So now we kind of know where we need to be with it. I'm going to hold it down and just kind of cut it off to size a little bit. Let's make like a score mark where I want it. And then I'm just going to take a pair of wire cutters and cut it off at that shape. Okay, here goes nothing. Let's see what kind of mess we can make of it. And there it is. And that should hold pretty well. And in that way, that solder can flow around there and it makes a nice solid joint. And you don't have to worry about lifting up on the tracks. So that's how you patch it. This is a trick that I use a lot on things that have been serviced. When a circuit board's been worked on a lot or has the tracks burned up or something like that, this is a good little technique you can use to make up little tracks to repair it. If you remember those bodge jobs on the bottom of that Marantz 2500 and the tone control board, there were 3 different places where I actually used this technique to repair it, and it turned out almost perfect. You can't even tell. So there you go. Let me finish wiring these all up and then we'll be back. Okay, everything's wired in here. So the next thing we want to do is we're just going to do a little static test. So the first thing we're going to do is put our meter on diode check. And we're going to check from pins 8 to 10 and 1 to 3. And we want the black lead on pin 8, the red lead on pin 10, and we should read about 2 diode drops, which is about 1.2 volts or so. And you can see there it is. Same thing here, red lead on 3, black lead on 1, and again 2 diode drops. And we should see that on both chips. Yep. Yep. Now this by no means is a perfect test, but this is just a little static test that we can do to make sure that at least the transistors are installed correctly and that they're reading correctly and that there's no shorts. Once we get that, we should be fairly confident that we could at least apply some power to this. And again, we're going to use our dim bulb tester, and we're just going to see if this thing will come up. Okay, we got everything finished up here, and a couple other things we had to do. First of all, if you remember, we had these messy resistors here, and we had this one here that had been jumpered out. You can see. So obviously they needed replaced. These are 0.22. The ones that I installed were a 5 watt instead of a 2 watt, or whatever these are, and they are 0.1. Now, I never would suggest to change the value of a current limiting resistor unless you really know what you're doing and understand how it affects the circuit. These are actually put in there in line with the output transistors and in line with the speaker. And if something goes wrong, number one, this will limit the current a little bit. Number two, if you have too much current, they'll open up and pretty much act as a protection circuit. However, these components in here, if you remember these little Darlington packs, these are rated at about 50 watts maximum. Whereas the components on here, these output transistors, are good for 200 watts of dissipation. So they're much heavier components than what was in there. And these modules can each run at, easily run at 80 watts per channel, but can even run as high as 100 watts per channel under the correct conditions just by increasing the voltage on them. So by reducing that current limiting resistor, it'll allow a little bit more current. It may a little bit, and again, these are all marginal, not big differences, will change the damping factor a little bit possibly. But more importantly though, by changing that value, you no longer can use the recommended values in the book when you're setting bias. The bias of these circuits, according to the person who made these, you want these to be biased at about 34 milliamps. And you do that by measuring across these resistors. So by measuring the voltage drop across these current limiting resistors, we can actually calculate how many milliamps of current, of idle current, is flowing through the circuit. So obviously when we go from a 0.22 ohm resistor to a 0.1 ohm resistor, that formula is going to change. That ratio is going to change. So long story short, if we measure across one of these, we should see about 3.4 millivolts if we want 34 milliamps, because we want 34 milliamps, which is 0.034 amperes, and we want it across a 0.1 ohm resistor. And remember, voltage equals current times resistance. Okay, so V equals IR. So if we take 34 milliamps times 0.1 ohms, that would equal 3.4 millivolts. Now if we measure across both of them, because there are two of them in the circuit, then it would be double. So we should see a drop of about 6.8 millivolts in here. So that's what we want to set our bias. Now, Pioneer was kind enough when they created this circuit board, they actually put two sets of holes for these resistors so that it can accommodate different components. Part of the reason that Pioneer did this, and a lot of their stereos they do this, they have some different layouts so that they can switch components during production without having to redesign the board. Now what this does for us is that gives us an extra set of holes where the resistors are not populated. And what I did was, by taking some of these are just little header plug, and if you notice they're scored, you can actually break them off to what size you need. I took 6 of them and just snapped them off, and I stuck them in those empty holes, and those now have given us some nice test points so that we can measure our bias. So if we go from the center to either one of these, we're reading across one resistor, okay? The center to either one of these. If I go from end to end, that'll give us the drop across both resistors in series. So we should be able to measure our 3.4 millivolts here, and we should be able to read our 6.8 millivolts here. The other thing is, if we have DC offset at the speaker terminals, which these are your speaker terminals here, the green wire, the yellow wire, and the black. Black is your common, yellow and green is your right and left channels. So if you measure across here, this is where we can actually measure at the speaker what our DC offset is. But we can also look at DC offset from here by measuring and comparing the difference between these. If you have no DC offset, theoretically, both of these should read the same. So I should have 3.4 and 3.4, and then a total of 6.8. So the original design with these chips did not have a bias adjustment. Now with these new modules, we actually can adjust our bias. It did have a DC offset adjustment, which is on the opposite side of the board, and we can adjust that as well. So now that we have this all configured and we know what voltage we want to set this for our bias, remember we want 3.4 millivolts from here to here or 6.8 from here to here, we can now check and turn this thing on and just see if we have it. Okay, we're once again set. We have a dummy load on there, and we have our current limit set. And we're going to turn the power on with our current limiting bulb. And we should get protect relay. And we did there, it just clicked. And now before I go to full power, I'm just going to take a rough measurement. You want to start with these pots turned counterclockwise. Counterclockwise turns the bias down, and clockwise turns the bias up. So if we go from our center to our first post here, and you can see we have 1.5 millivolts here and almost nothing here. So first of all, this one's got some DC offset on it. Let's check this other side as I bump the camera. Alright, and if I go from here to here, and you could see very low, and if I go from here to here, again very low. So none of these modules are actually turned on very much because the bias is turned down almost the whole way. So let's start by measuring this first one, and let's see if we can get the bias to turn up. Get a screwdriver. Okay, here we go. Remember, we're looking, oh yeah, it's increasing. And even with a 10-turn pot, it can be very touchy. Okay, so there's 3.4 millivolts, and if I go to this side, it's 1.9. So if you notice, they don't match. And if you look there, there's your total. Now, if we go from here to here, this yellow wire, you can see there's your DC offset. That's the speaker terminals. And that coincides with this. So we are going to have to set our DC offset on the other side. But that's not too terrible. It's not bad. Let's check this side now. So again, I'm going to go from here to here. And you can see it's very low, and we're going to adjust our pot and see what happens. And it's adjusting. And you'll see you hit a certain spot where it starts operating, and then it'll adjust very quickly. So you really don't want to crank on this pot. Okay, that's close enough. Now let's go over to this side. And if you look at that one, it's very close. Almost 3.3 millivolts there. And about 3.4, so they're very close. And if I go from end to end, there's your 6.74, so that's almost 6.8. So this side's good. This side's a little bit out of DC balance. So we just need to adjust the offset on the other side there, on the other side of the board. The good news is it works. Now I have my dim bulb on there still. If we go, I think we're safe to go to full power now. And what I'm going to do is I'm going to monitor this, and we should see the bias go a little bit up. See, it's a little high right now. And you can see it went up another 1/10 of a volt when we went to full power. So again, with these big heavy-duty components, you have a lot of leeway. So even if you bias this a little bit hot, it's not, you don't need it, it's not, so forth, but it won't harm the circuit. This is a very forgiving circuit. So far, I am very impressed with the design of this thing. So let's flip this thing up on end and see if we can't get the DC balance set on this channel. Okay, so we now have this set on. And let me see if I can find a adjuster here. And we want to try to get this down to 0 volts. So these two blue pots here is the left and right channel. Left channel is the one with the problem. And I'm across the speaker terminals. You can just barely see it behind the meter there. See my red lead? And we're just going to adjust this the wrong way first. And you can see it's zeroing out very well. Now, adjusting DC offset is kind of touchy because you have to move it a little bit, and you have to then let it settle. So you can see it goes from positive to negative. So you go from one of the transistors being biased too high to the other one being biased too high very easily. And what you're never going to get 0. You want it to be a single digit of millivolts. So anything between 1 and 3 millivolts I consider to be a good DC offset. So that would be a very good DC offset right there. So that's all it really took, was that tiny little adjustment. Now let's go to the other channel, and if you recall, it was pretty darn close. But we'll go hook it up as well. And you can see it's pretty good already. We can maybe try it, but all we're going to do is throw it out of whack and then have to get it back in. So we'll take a look here. That's the wrong way. You notice I always go the wrong way first. That's just the 50-50-90 rule. If there's a 50-50 chance of you doing something, 90% of the time you'll get the wrong 50. That's our rule at work. Hey, how about that? Walk away. Okay. And this will bounce around. As long as it stays in that couple of millivolt range, we're good. So all is well. Now we can go through and we can fine-tune our bias once again. So when you set bias, you really want this thing to warm up for a good 10 minutes or more. and then adjust your bias. You can't adjust it on a cold system. So we're going to just let this cook for a while, and then we're going to set our bias once again. Okay, now we can try our module out here. We have our dummy load connected. We have a 1 kilohertz signal going into both inputs in the auxiliary jack. We have our bass and treble set at center. Everything's centered up. So let's turn this up and see what we get. Here comes our fundamental on the left. Look at that. Okay. Now, the thing I did see that I didn't like, when it was starting to getting a wee little bit of oscillation there, but not bad, and that's only at maximum volume. Let's turn on our voltmeter and see what kind of output we're getting here. If my mouse will, of course, behave itself. Okay, my keyboard is on the fritz. Let me fix that. Okay, we're going to watch our volts RMS. Remember, it's times 10. And we'll bring it up just till we start seeing clipping on the FFT on the red trace starts getting extra bumps. All right. Right about there's where it's starting to go. So 21.8 volts. 59.4 watts. Not bad out of a 45 watt per channel receiver. And these aren't even getting warm. They're not even, I mean, they're not even lukewarm. I mean, they're just above room temperature. So, hey, I think this is a success. So, everything works. The owner of this wants me to recap it and change a bunch of stuff in it, so I'm going to do that. I won't do that on camera because you've seen that a million times. And I'll get all the boring stuff done, and then we'll come back and give this thing a real workout. Okay, we got her all back together. And it's playing pretty good right now. Everything's looking good. You can see we got it all recapped. We got the new current limiting resistors. We upgraded the power supply a little bit with some bigger transistors and some better heat sinks. Redid the tuner. Put a new set of Nichicon audio quality filter capacitors. So all the little things that needed done. So a couple of transistors were replaced, a few things like that. So this thing's ready to go. Now we'll just do a quick little test on it, check a couple little factors, and then what I'm going to do is I'm going to end this video right here, because what I'm going to do is, this is a really good candidate. The way this tuner is laid out, it is a very good candidate to do a little video on tuner alignment. And what we're going to do is we're going to use some of the gear that a lot of you have asked about. I've been getting a lot of questions about how to connect up certain pieces of test equipment, like the Sound Technologies 1000 or the SG-165 Sencor unit. We are not going to use our new leader LSG-216. I'm going to use the stuff that you guys have been asking questions for. So if that sounds good, stay tuned, because there'll be another video following up where we do the alignment on this. And it's going to be more about using the test equipment than it is aligning this particular tuner, because really this tuner's performing really well, and I don't really think it needs a whole lot of alignment, but we're going to go through the motions anyway. This turned out really nice. we're going to do a couple tests here. What I will say is I've been listening to this for a couple hours now, and I really don't notice a big difference between the STK chips. That's actually a really good thing, because those STK chips, whether you believe it or not, they really have good characteristics, good sound quality, good performance. Sanyo really did a good job with those. If you get the original ones from Sanyo, they're not by any means cheap or whatever compared to the discrete components. These are essentially the same as discrete components, except they're all on one substrate, and that makes them all thermally coupled to one another, which helps with thermal tracking and everything. This is actually an advantage to have these. And what I will say is the guy that came up with these little modules under here really knew what he was doing, because he pretty much duplicated these chips with discrete components and even improved upon it. So the modules are very universal. They'll work on a lot of, from the 0030, 0040, 0050, clear up to the 0080 STK chips. It will work right in. It'll be a drop-in replacement. The only thing you have to be careful is some of the STK chips use what's called a quasi-complementary amplifier design, and these are actually complementary, full complementary or complementary symmetry amplifiers. And although you can substitute one for the other, these chips, you got to know what you're doing. There are some changes you have to make. There are some different things that you have to adjust. But anyway, enough about all that. Let's do a couple tests, and then I'm going to close out this video and start working on the alignment video. Okay, we already saw the sine wave on here, and we saw that clipping was clear up around 60 watts, if I'm not mistaken. So let's take a look at our square wave. And the main thing I'm worried about on these is I don't want these modules to break into oscillation. That's, you know, anytime you change a circuit like that, you got to kind of worry about that. So we're going to check some stability by putting a square wave on this, and we're going to just look at the rise and fall on the, you know, in the edges, and just see what this thing does. So here we go. And you can see there's a teeny little tip at the very beginning, but you can see how nice these are. There's no oscillation, nothing. Not bad. Of course, we were driving it into clipping. That's a we're way over driving this thing right now. And you could see it was rock solid stable. So let's set up another test now and just check for linearity. Okay, I have an audio sweep set up, and we're going to go from 10 Hertz up to 20 kilohertz, and we're going to try to keep right around that 15 volt range or so, and see what we got. Here we go. Remember, the reading down there is times 10. And in a perfect world, that would stay right on that. This number will stay pretty steady. And if you notice, it is staying very, very steady all the way down the line. So this amp has a really flat response. So far, so good. And we've kind of been punishing this thing a little bit. And if you notice, well, you don't notice because you can't feel it, but this heatsink is not even lukewarm. I mean, it is barely getting warm. So that's fantastic. Everything's staying really nice. So these modules, I'm giving them 2 thumbs up. They work really well. All right, let's shut that off. And we'll be right back. Okay, our next test, we're going to check, we're just going to check the peak power of this, the dynamic power. In other words, this is going to simulate, at least somewhat, a instantaneous peak, like the kick of a bass drum or some deep note that hits really hard, really fast. And we just want to see how much storage this power supply and how much energy this thing can release just for a split second. Now, this is not your RMS power. In other words, this is not what the amp is continuously putting out. This is what it's capable of before it distorts the signal. You know, with a, like I said, like a kick drum or something. So right now I have it set to capture the image and store it. And so what we're going to do is we're going to take a shot. So we're going to, this is just basically what my signal generator is doing, is it's going to put a burst of 20 hertz. It's going to give one cycle of 20 hertz. And the scope's going to capture it. So here we go. And you can see there it is. It captured it. And if you look right there, it's a nice clean signal. Now, don't pay much attention to the little fringes here. This is the noise that's on the oscilloscope itself. It's just one of the limitations of these lower cost scopes. And what we're going to do is we're going to keep increasing the volume and increasing the output power until this thing clips on us. Okay, and you can see we're getting an instantaneous burst of 23.8 volts. Okay, so let's just keep going till it clips. A little more. Okay, that's a little too much, so let's back it off. Right there, and you can see it is clipping. So this is very interesting. So what you're seeing here is, for a half of a cycle of 20 hertz, the amplifier is able to sustain this volume level, and you can see it's 32.6 volts. Now, just to give you an idea of what that is watts wise, okay, 32.6, 132.8 watts. Now, that is not RMS. That is peak power. And do you ever see these amplifiers that have these ridiculous power ratings, especially like car stereos, where they say maximum peak out power? This is what they're talking about, and they even stretch the truth on that. But this amp, for just an instantaneous second here, it can actually withstand or dissipate 138 watts. Now you can see when it's time to do the other half of the cycle, at that point, you can see this is where the power supply, this is the capacitor bank railing out on us. So the caps are not charging back up. That's what this is. In other words, the power supply is unable to recover the capacitor bank to get the full cycle out. If we go down a little bit more, you're going to see that's going to smooth out. See, it's starting to smooth already. I'll bring it down a wee little bit more. I'm just barely touching it. And right about there, it's nice and smooth. There's just a wee little bit of distortion. This is right at the point for this one cycle that the power supply cannot handle it. But it's important to understand that these modules and the circuitry is easily handling this. It's the power supply that's your limiting factor. So that's why it's not worth putting, if you put a 200 watt transistor in there, it's not going to make any difference. The amplifier is only as good as the power supply. Okay, so if we look at this, we're getting a pretty, it's holding its own right now at 26.4 volts. Which is about 87 watts. So, and that's 87 watts peak. That is not RMS, okay? This is peak power. This is not RMS, okay? And I know people get kind of hung up on the saying RMS watts. That's not a real thing, but the voltage is actually, we're measuring peak, not RMS. So, anyway, right there is about the maximum that this thing can handle. And the idea that I'm trying to show here is that in a well-designed amplifier, you should be able to go beyond your maximum RMS power for just a split second. That way, if you're running the amplifier at a loud volume and a heavy bass passage comes in or something, the power supply can actually sustain that and maintain it without distorting. That's the difference between a 50-watt amplifier that sounds distorted when you're playing it at 50 watts and a 50-watt amplifier that sounds clear as a bell when you're running it at 50 watts. There it is. We just saw it right on the screen. So I hope that was interesting to you. All right. Well, that's the end of this video here. So what do you think? In my opinion, from my experience, these modules were very easy to build. They were very easy to install. They adjusted and calibrated very easily. And they perform every bit as good, if not better, than the original Darlington power packs that they're replacing. So all in all, I give this a 2 thumbs up. I think it's a great product. And the other thing is, if you have an SX-780 like this, or if you have any of the old Fisher amplifiers, a lot of the old ones that use these Sanyo STK chips, you can now give it a new lease on life by putting one of these modules in there. So now we have an option without trying to worry about getting those knockoff phony STK modules that are out there. So, man, this is a great product. I really like it. And again, I'm not being endorsed by this. This is something that a viewer sent to me to try out. And he sent me this receiver and kind of wanted me to go over it. I really hope he's going to invest the money and order a really nice walnut case for this thing, because it's going to be a wonderful amplifier or receiver for anybody who decides to have it. So, or for him if he's going to keep it. So, all in all, great product. This was really fun to do. I think many of you, if not all of you out here, are capable, just with basic soldering skills and so forth, of building this little module. You could see how easy it was to install, and you can have a really nice little receiver here. So again, I wish you all peace, joy, happiness, and good health in your lives. And as always, stay well. And we're going to do a follow-up video here, doing a little demo on how to align FM, or the FM tuner in here, using an alignment generator. Okay, take care, and we'll see you next time. Bye-bye.